Okay, this is also nice. Imagine this is a tank of gasoline, the one that you put in your car, right? And this is open to the atmosphere, open to the environment. We call this the exposed surface or the free surface. We're going to use this term a lot. So this is the free surface. If a container has an interface between air and water, or interface between the fluids, and it's exposed to the environment, then you call this the free surface. A good example, for example, is a river has a free surface that is exposed to the environment. The sea has a free surface. A glass of wine or a glass of piscola, right? You have a free surface. You have an interface between air and liquid that is exposed to the atmosphere, and it's exposed to the atmospheric pressure of the place that you are. It is useful in these cases to use a reference pressure, the pressure applied to the free surface. I just told you before, frequently the atmospheric pressure. So if you say that this is the atmospheric pressure that you already know by reading the news, then the pressure at here or here could be easily computed. Let me erase this and re-explain this. So imagine that you know this pressure, right? The pressure at this point, at this surface, is equal to, let's say, P0, atmospheric pressure. So if you want to know how much pressure you feel here, it's basically the pressure here plus the pressure generated for this by this column of water. And you know how to compute that. The pressure in this point then will be equal to gamma times h, where h is this distance between here and here. This is h. Oh, this is horrible. This is h. This distance is h. Let me rewrite. This is terrible. Okay. So you want to know how much pressure you feel at the interface of water and gasoline. You know, this height, we call it h, right? You know this height. And so basically, and we know that gasoline has a gamma that is known, specific weight. So if you know the pressure here, and you can compute the pressure here with this equation. The pressure P that you're going to be feeling here is equal to the pressure generated by the water column with this height plus the pressure at this point. Okay? I hope you were able to understand this. So, what I wrote here, it is useful in these cases to use as a reference pressure the pressure applied on a free surface, frequently the atmospheric pressure, which is what we feel here. And the other important thing is, if I ask you, can you tell me the pressure at this line? Or can you tell me the pressure here, here, here? Would you say this pressure is different? So this pressure is feeling this, this pressure is feeling this, this pressure is feeling this. Think about it. Is this pressure different from this one? Is this pressure different from this one? And is this pressure different from this one? 1, 2, and 3. Remember we said that, let's say this is x, dp dx is equal to what? It's equal to 0. What is this equation telling us? That the changes in pressure in the x direction, where this is x, they don't change. There's no difference. So the pressure here is equal to the pressure here. It's different to pressure here. So all 3 points feel the same pressure because the pressure is given by the height right here, and this distributes equally in the horizontal. The only changes in pressure are if you go down or if you go up. Because in Z, or the vertical, is the only direction you're gonna be feeling changes in pressure. Understood? Very important, very important. Keep that in mind. Changes in pressure in the horizontal do not change for fluids at rest. So the pressure on a homogeneous, let me have my pointer here. The pressure on a homogeneous and incompressible fluid at rest depends only depends only on the depth of the point of interest relative to the reference plane, and this is the reference plane. This pressure does not depend on the shape or geometry of the tank containing the fluid. Whenever you have if you have a triangle and you are measuring the pressure 1 meter below a triangle of water, a square of water, a sphere of water, if you're measuring 1 meter below and it's the same fluid at the same temperature, same pressure, no changes. Okay, now we talked about this in the previous unit about gauge pressure, atmospheric pressure, and absolute pressure. So basically, a common criteria is that whatever you measure, for example, in your tires, in your bike tire and your car tire, is usually relative or gauge pressure, also known as manometric pressure, right? If you measure with your PSI measurement, measure meter or pressure meter, you're gonna find the relative or gauge pressure, manometric pressure. If you want to know the value of the absolute pressure, then you have to add the atmospheric pressure at that place. If you're at Calama, you're going to have one atmospheric pressure. If you're at Antofagasta, you have a different pressure. Okay? Atmospheric pressure represents the effect of the atmospheric weight per unit of surface. We talked about this. It depends on the weight with respect to the sea level, temperature, density, and wind. A barometer, which is something you probably have heard about in the news or someplace or when you were a kid, measures the absolute atmospheric pressure of the place that you're measuring. And the atmospheric pressure, as we said or we talked about in the previous unit, is 1.01325 bar, 101,325 pascals or 101 kilopascals, 760 millimeters of mercury, 10.34 metros columna de agua, or basically the easiest, 1 atmosphere. This is the measurement at sea level when the atmosphere or the temperature is at 15 degrees Celsius in a place in the world that is 45 degrees latitude. This is what is known as the standard atmospheric pressure. Let me erase this here. Let me present you the barometer. Barometer, student, this is the barometer. The barometer is like you see here, it's a container that it's open to the atmosphere, that is filled with mercury, and you put an inverted tube here, as you can see, inverted tube, and you put a ruler here. This is what people in the age of Newton did in order to measure atmospheric pressure at different places. And the atmospheric pressure would push the mercury up in this tube. There's going to be vapor of mercury that is going to be evaporating here. And if we know the pressure of the vapor, which we can know by tables, and we have point A and point B, this is open to the atmosphere, this is basically atmospheric pressure. So, and you know the pressure here, if you want to know the pressure here, you, with the height and using the equations that we've seen, you can compute the atmospheric pressure. This is called the barometer, okay? Or piezometer too. So a pressure that you need to compute, and if you know the height and you know that the pressure here is atmospheric, you can compute. So this is plus P0 or atmospheric divided by gamma. But if you say this is 0, it's not 0. This is not important. I'm just going to focus on relative or gauge pressure. We don't need to compute atmospheric absolute pressure. We just leave this place. And if you know H, you can compute the pressure at A. And if you know the pressure at A and you know the fluid, you can compute how much it's going to go up. This is a piezometer or simple manometer. A differential U-tube manometer, it's one that where you have pressure A and pressure at point B, and you have different heights, and you have 2 or 3 or more fluids. It could be mercury plus water plus oil, and they change in height, and you can compute the pressure, for example, at B, if you know the pressure at A and the differences in height in different columns. I'm gonna do an exercise for that too in a different video, and you can compute the pressure at B knowing the gamma of each fluid, the heights of the columns, and the pressure at one point. And this is the exercise I'm gonna be doing in another video. So I'm gonna finish here. Or let me see here. No, I'm gonna finish here, and I'm gonna give you 2 more videos. One video showing you the wedge demonstration of how the pressure at a point does not change in any direction. Then the other derivation that shows you that pressure in the horizontal plane does not change. The only changes that you feel in pressure in a fluid at rest is in the vertical direction, and it's only given by the weight of the fluid. And let me see what I have in the next slide. Okay, so we leave it here. We are gonna finish our first video here. See you in a few more videos ahead.